All right, thermochemistry. These are your notes. Just a few things. Thermodynamics is the study of energy and the transfers accompanying physical and chemical changes. Remember, anytime you see therm, we're talking about heat. Okay, we're talking about a lot of heat with this. A couple things with this: endothermic and exothermic. Endothermic means you take in heat. I think of this as you enter a building. You're entering a building. Endo, you're taking in heat. Exothermic are things that release energy. Okay, exo, if you exit, you leave, you release, you go out. What? Are we supposed to be copying? These notes are already posted. I posted these last week, I think. Okay. No, Monday. So exothermic. Some other terms, thermodynamic terms. A system is the substance involved in the chemical and physical change that we're studying. The surroundings are everything in the system's environment. Okay, everything in the system's environment. The universe is everything. Okay, just like the universe is everything. Your surroundings. So if this is our system, if I'm studying you, your system would be the other people in here and everything else in here. Okay, and even maybe the outside weather, but the universe would include what's going on in Japan right now. We're talking about the heat and stuff like that. An open system is the things which matter and energy can be transferred to and from the surroundings. In a closed system, only energy can be transferred to and from the surroundings. Now, notice there's no matter. Okay, are you an open or closed system? Open. They're open because you transfer matter. Okay, matter and energy are transferred into you and out of you. Okay, we are an open system. A closed system, you would not be alive. You try to do some things to make some things closed systems sometimes. Okay. When you, like I said, a bomb in a way is a closed system. Okay, you don't want matter to leave it. Maybe you want some energy and things like that. An isolated system is what really a bomb is, I guess, more so than that, in which matter nor energy can be transferred to and from the surroundings. Like the bomb we're going to make we're going to do coffee cup calorimetry. It'll probably be a closed system. We tried our best to make it an isolated system. Okay. So when you say closed and isolated, it can be, it's just not under normal circumstances. What do you say that? Say it again. Okay, so for the isolated, it says neither matter nor energy can be transferred, but it's transferred. It's transferred. Can be. It's however you want to say it. Good question. A state function, okay, is the properties of a system. The value of the state function depends on the state of the system and how you got it that way. If you will notice, on that appendix K I just gave you, okay? That gives you some things that states, and you'll notice that C2, let me find one. C, carbon, depending on what state it's in, has different values of delta H, okay? And delta S and delta G. You see, graphite carbon has a delta H of 0. Diamond graphite has a delta H of 1.897. Carbon gas has a delta H value of 716. Okay, so they depend on the state. Okay, they depend on the state. PV and T are state functions. Okay, PV and T are state functions. In this class, delta H, delta S, delta G are also state functions. When you see like the little, we'll get there in a second. Well, 3 laws of thermodynamics. The first law of energy is constant. Okay, energy is constant, also known as law of conservation of energy. Number 2, and sometimes you see the thermodynamics broke down into 2 laws. Okay, sometimes you see thermodynamics broke down into 2 laws. The first law is known as the law of energy. The second one and the third one can sometimes be combined into 2. Okay, the second law of thermodynamics, saying a spontaneous system, the universe tends towards a greater state of disorder. Okay, disorder, I don't know if you remember from your vocab, is entropy. Disorder is entropy, but the entropy of a pure, perfectly crystalline substance is 0 at 0K. That's a very important thing. Okay, at 0K, something is not moving, so it is not disordered. Okay, things are disordered. Number 2, because they're moving. Okay, the faster they move, the more disorder, i.e., the more entropy. Okay, the slower they move, the less entropy. Yes, ma'am. Are we still taking that vocab? No, ma'am. Thermochemical equation is the balance equation with its value of delta H, okay, with the value of delta H, the coefficients. Now, this is kind of different, okay? Thermochemical equations can have fractions, okay? When we've been balancing equations, we have not been dealing with fractions, okay? In your chemistry life, and in thermochemistry, you can have fractions. If the heat is on the reactant side, it means you must have heat put into it, so that is an endothermic reaction. If the heat is on the product side, it is exothermic, okay? It's heat, you're releasing heat. Example, okay, is that endo or exothermic? Exothermic, because it releases 1,300 joules of.
So that can be added into a chemical equation?
Mm-hmm. That's thermochemical equation,
A thermochemical.
Mm-hmm. Which, yeah, the thermochemical equation is a more descriptive equation. In a thermochemical equations, the states are extremely, extremely important, okay?
So the solid and the What does the G mean?
Yes. There we go. Indicates number of reactants, the number of moles, not the number of molecules, okay? The numerical value refers to the number of moles of the substance. Okay, there's 1 mole in the delta H. When it gives you the delta H, notice you had 1 mole of what you started with, okay? 1 mole of ethanol. The physical states are important and must be specified. I just said that. Delta H typically does not change with moderate temperature changes, okay? There will be some. We'll get into that a lot more at the end of this unit. Mass to energy. Mass to energy is used to determine the amount of heat that is released to absorb when given mass reactants. Working like a stoichiometry problem, the mole ratio. So you convert from grams to moles, okay? Convert from grams to moles, and then you multiply by heat over the number of moles known. You get that known moles from your balanced chemical equation. So an example of this, so I'm going to take 10 grams of S8, okay? 10 grams, well, I got to write my equation first, okay? I write my equation first. I balance my equation. I'm going to take 10 grams of S8, okay? Put it over 1. I'm multiplying by 1 mole over the molar mass. I remind you it's S8 because sulfur is a polyatomic element. And then my next step, what's my next step going to look like? I know my heat's going to be on the top, so 296.8 kilojoules is going to be on the top.
1 mole S8.
1/8 of a mole of S8. 1/8 of a mole.
Where do you get this? I know there's. Where do you get the 1/8? Like, how do you?
I just balanced it. So I know I had 1 mole here. I had 1 S here, and I had 8 here. So, you know, it's typically we need to put an 8 in front of this, okay?
Yeah.
But you just don't do that thermochemical equation. Because you want to have 1 mole. You want it to be as reduced down as you can. That's why we can use fractions.
So we reduce. Reduce kind of.
Yeah. And it equals 92.6. Okay. Fairly simple. Enthalpy change, the other thing we're going to do today, you're not going to have any mass to energy homework today. You'll have some tomorrow. Enthalpy change, enthalpy means heat, okay? Enthalpy is the measure of heat. When we just, delta H stands for the change in enthalpy. And once again, delta stands for, delta anything in science stands for change. H being the enthalpy because enthalpy is heat. I don't know why we use the term enthalpy instead of heat. Not really sure about that answer, but delta H is the enthalpy heat. Here's the key thing. You're going to see this a lot. Delta H is products minus reactants, okay? The sum of the products minus the sum of the reactants. Sometimes called the heat of reaction, okay? If delta H is negative, it is exothermic because you are losing heat. If delta H is positive, you are endothermic, you are absorbing heat. Are most reactions endo or exothermic? Exothermic, because most reactions give off heat, okay? Most reactions give off heat. Well, just hold that thought till next week, okay? Just hold that thought till next week. We will explain that. Most state, okay, thermodynamic standard state, okay? This is not, now here's the thing. Thermodynamic standard state is not the same as STP. We know STP, standard pressure is 1 atmosphere, standard temperature is 273.15, okay? Everyone remember that? This is different. Thermodynamic temperature is 298 Kelvin or 25 degrees Celsius, okay? This is different. You'll notice at the top of your paper, and it's really 298.15. Just not on here. Notice the top of this paper, it gives you the values at 298.15 Kelvin. Okay. Standard thermodynamic temperature is 298. Pressure is still the same though. Okay. Pressure is still the same. Now, why 25 degrees Celsius? Why are we talking about things being 25 degrees Celsius? What's the significance of 25 degrees Celsius?
Below freezing.
No, 25 degrees Celsius is above freezing. 0 degrees Celsius is freezing. 32 Fahrenheit is freezing. Okay.
Oh, okay.
What's the significance of 25 degrees Celsius? Anybody? It is what's considered normal room temperature. Okay. Room temperature, when they tell you to let something get to room temperature is typically determined as at 76, 77 degrees Fahrenheit. Okay.
Oh, that's 77 degrees Fahrenheit.
Yeah. Mm-hmm. That's what room temperature is, and that's what thermodynamic standard temperature is. Like I said, this is a minute, really not recently, it's about 15 years. Technically, this has changed to 1 bar, which is 0.987 atmospheres. I don't know who made that change, but we still just use 1 ATM. And notice 1 ATM significantly is the same. Okay. For the standard state, so something that's a pure liquid or solid, you use it in solid or liquid. So we're talking about gas, the partial pressure must be 1 atmosphere. For substance solution, the standard refers to 1 molar. Okay. So you have 1 molar at 1 atmosphere. Okay. If it's a solution. Standard enthalpy formation is really what we're getting to today. Same thing. Now, this little circle, the degrees thing, means standard. Okay. That's what this little thing means. Okay. It is the standard delta H. Okay. The standard enthalpy. That means, guess what? You can use this. The heat of formation is determined experimentally. The standard heat can be determined mathematically. There we go. It's called the heat of formation. Here's the big thing. And I mean, you can use this. You're going to use this, or I'll give you the value. But you'll notice that any element in its natural state, the delta H value is 0. Now, that's different from the third law of thermodynamics. The third law of thermodynamics talks about entropy, something different, okay? Entropy, something different. So if you look at aluminum metal, its delta H value is 0, okay? O2 gas, because that's how oxygen typically is around, isn't it? It says, oxygen diatomic element, and it's a gas. Its delta H value is 0. So that is something that can be very important if, you don't have enough time to think about it, okay?
So anything at its more natural state is
Any element at its natural state is 0. Any element. And that includes our diatomic and our polyatomic elements, okay? Includes our diatomic and our polyatomic.
Wait, our polyatomic is like
Polyatomic elements, P4SH.
okay.
P4SH. Examples, write the equation that represents the standard enthalpy formation of CH3Br. Okay? So, my product is going to be CH3Br, isn't it? This is very different, okay? I have to use my standard thing. So we know carbon's form, I break this down into its elemental form. If I'm going to write, I could write CH3Br, the formation of that, with a different reaction, okay? But because we're talking about the standard enthalpy of formation, we break it down into its pure elements, okay? Break it down into its pure elements. So carbon, if you want to go look, how did you know what carbon to use? You wouldn't see which thing had a delta H value of 0 of carbon. And that would have been graphite. Hydrogen, now notice this is 1.5 hydrogen, isn't it? Because I need 3 hydrogens total. There's always going to be a 1 here, okay? There's always going to be a 1 in front of this. And if it's breaking down, it'd be this would be the reactant, okay? But I need 3 total. So I multiply what number times 2 equals 3, and that's 1.5. And hydrogen is naturally a gas. Bromine, I need 1 of them. And so I know bromine is diatomic, so I need 1/2 of a mole of bromine. Okay?
What is diatomic?
You said there's those 7 diatomic elements. Hydrogen, nitrogen,
Oh, yeah.
and once again, dealing with moles, not molecules. So, let someone do this one for me. Just tell me verbally what the answer is. NaNO3 solid. I want you to write the standard enthalpy of formation of NaNO3 solid. is nitrogen simply. So I have 1 NaS plus 1/2 into what state is nitrogen? Gas. And how do you get this information? Carbon's the weird one. It can be a diamond or a graphite or a solid or a gas. Okay. We can look at our periodic table and we see that it gives you the states at 25 degrees Celsius. Okay. So we know that nitrogen is a gas. I think it's green on your periodic table. I think it's green on your periodic table. Plus
1/2 O2.
1.5 O2. Or you can say,
Yeah, 1.5.
or I'd probably write 3/2 O2, and that's a gas, yields NaNO3S. Okay. Everyone understand how we did that? We just break it down. This is what most people try to do when they start doing decomposition or synthesis reactions. They try to break it down to its elemental form. Like I think of us when we first started doing it, like some people, when you write down the decomposition of calcium carbonate, you'd write Ca plus C plus O. Okay, that's how you would do it here. So if I wanted to do the decomposition of calcium carbonate, the standard enthalpy of formation of calcium carbonate, it would be Ca solid plus C graphite plus 3/2 O2 gas goes to CaCO3S. Okay.
So how come our Thursday quizzes are why don't they do?
Because we're just talking about chemical equations, not thermochemical equations. Okay.
But I'm saying what we're learning.
Because the AP exam asks about chemical equations a lot, and you will have some thermochemical equations to write, but not near to the extent. When we do a stoichiometry problem, we don't use a thermochemical equation. We do a chemical equation. All right, so we found my mouse. There we go. We got that right. Like I said, you could have written 1.5. I would have written 3/2. Okay. Standard enthalpy for reactions. Okay. Is delta H standard RxN. Okay. Saying kilojoules per mole, or sometimes just kilojoules. Sometimes called the standard heat of reaction. This is the big thing. Okay. This is the big thing here. This is the big equation for this unit. Okay. So same thing Hannah tried to write down a while ago. H equals delta H equals H products minus H reactants. This is a more specific equation. Okay. Delta H standard of the reaction. So the standard enthalpy of reaction equals, this thing is the Greek letter sigma. It means the summation. Okay. It's the summation of the number of moles of the standard enthalpy formation for each one of the products minus the summation of the moles times the standard enthalpy of formation of the reactants. Okay. That's the big thing there. And you're going to see what's so nice about this unit is we're going to talk about delta H today. We're going to talk about delta S tomorrow. And we're going to talk about delta G on Monday. And guess what? Only thing different in all three of those equations is I want to find the delta S of the reaction. I just use the delta S values instead of the delta H values. If I want to find the delta, and you'll notice that your thing has delta H, delta S, and delta G on the top of it. Each cap. So it's a very simple. You're going to use this a lot. Okay. Products minus reactants.
What does the F mean?
Enthalpy of formation. Enthalpy of formation. Yeah, it's what's given. It's the value that's given on here. Okay. It's the value that's given on there.
So the F is the 0 and stuff.
The F is the yes. All right. So examples. Find the standard enthalpy reaction. Enthalpy change for the reaction of HCl and NaOH solid. So in this, I need to write a chemical equation first, okay? Let me pull up my paint. This is going to be really crappy today. Still can't get my smartboard to work. Yeah, I unplugged them because that made me mad. No. That's the computer charger. Oh, those aren't for that. Those aren't for that. There's actually 3 there. All right, so the first thing I need to do is I need to write an equation. And it needs to be a balanced equation.
What was the question about the standard?
Find the standard enthalpy formation of HCl and NaOH, the reaction of HCl and NaOH. So I need to write my chemical equation. So NaOH, they told me it was a solid. plus HCl. And it was a aqueous solution. Yields, what does this make? NaCl, what state NaCl?
NaCl and H2O, right?
But what state of NaCl? Aqueous solution. Okay, aqueous solution. Aqueous solution.
So how can you use the aqueous solution instead of that solid?
Because this is a solid, because this is soluble. I put solid sodium hydroxide in a water solution of hydrochloric acid. Okay, so we know that this is also soluble. Okay, so but it's solid before it goes into solution. Okay, so I know from my solubility rules that sodium is always soluble. Okay, because I mixed it together with an aqueous solution. Plus, what state H2O? Liquid. Okay. So now I know that delta H, standard of the reaction, equals delta H of the products. What? This? RXN. Delta H of the products minus delta H of the reactants. And I missed the summation and the moles. I'll go back and put those in.
So this
is just my equation.
Is that equation the same as this equation? The long one that says the sigma thing?
Yeah. Mm-hmm. I put those back in. So I'm going to continue working this out very detailed, okay, on this example. So delta H of the reaction would be equal to, now, how many moles is it? I need to make sure this is balanced. Is this balanced right now? That equation balanced? Sure it is. 2 H's, 1 plus 1, 2 H's, 1 O. Okay. So, but I'm still going to show this in there. So I'm going to have 1, okay? And my products first, okay? My products are first. 1 times the delta H of NaCl plus, that's what summation means, okay? I'm summing up the products, plus 1 times the delta H of H2O. And it's H2O liquid, but I don't have enough room for that. I'm not that good to write that. So that's all my products, correct? So I've summed my products together. Minus 1 times delta H of H2O, because that's my second product.
So if it was like 1/2, you do.
You put a 1/2 instead of the 1. Whatever the coefficient is, which I think the next example has a coefficient in it. Okay. So I'm on my reactants, aren't I? So 1 times delta H of NaOH plus 1 times delta H of HCl. You don't have to show this step, okay? This is just step I'm just showing you right now to show where we're getting all these things, okay? The next step's when you got to show. So everyone understand what I did there? These 2 equations are the same thing, okay? I got rid of summation because I summed up the 2 products. I got rid of the summation. I summed up the 2 reactants. And the N stands for the number of moles. I got the number of moles from your balanced chemical equation. So now I'm starting ready to substitute some numbers in there. Delta H standard of the reaction equals, parentheses, 1 times, what's the delta H of NaCl aqueous? Where do you get that information from? This sheet right here.
Negative 407.1.
So times negative 407. Everyone agree with that? See where we got that? Plus 1 times, what's the value of H2O? Liquid H2O. That's a very big difference to make. This one? Where you see it? Here? Delta 1 times delta H HCl. All right, 1 delta H NaOH. Everyone agree that it's negative 285.8? Okay. Close parentheses minus 1 times, what about NaOH solid? What's that value? Negative 426.7.
Wait, what is it? NaOH solid? Yeah, negative 426.
1 second, Lamaya. I'm sorry, I did not hear you, Lamaya. Go ahead, ask it again.
Is it
An 8? Yes, ma'am. All right, and then so it was times negative what? I don't remember the number.
427.7, I think. 426.7.
7 plus 1 times what was HCl's? And this is HCl aqueous. Yeah, it is. Look under chlorine. Look under chlorine. Chlorine to find HCl. Yeah. Everyone see that now? Times negative. Well, I missed a negative sign there too. Oops. Negative 167.4. Now it's just simply put it in your calculator. It's just simply, you put it in exactly like this. I mean, I don't need the times ones, but don't forget your negative signs, okay? It's just simply, can you put it in your calculator now? And this is why I like those calculators like Balin has right there, because it shows you what you're doing, okay? I mean, the ones that show you what you're doing. So I don't like my phone as much on this one, because I want to be able to see my work, okay? You can do it with it, but I think it's easier. But typically the biggest mistake with this is someone just types something in wrong. They miss a parentheses or something like that. That's typically the biggest mistake with this.
So it's just going to be negative 407.1 plus negative 285.8, and then you add that to the product or the.
No. You do this one. You do. So I'll break it down like this.
Negative 98.8.
Yeah, I mean negative 98.8 is the correct answer. So you have
negative 407.1 plus negative 285.8.
Hold up, 285.8. Crap. 407.1. So you get so this side simplifies down into negative 692.9, okay, minus parentheses negative 594. That's a horrible 594.1, okay? And now we know that, simplify it some more, 692.9 plus, because two negatives make a positive, plus 594.1. And that equals, what did you say, Balin? Negative 98.8. What?
Negative 98.8.
Negative 98.8 kilojoules. I want y'all to work the next problem out yourself, okay? And I'll come by and check it. Actually, I'm not to make people mad that aren't in here. Let me